Okay, 7.3, applying similar triangles. So we're going to apply what we know about solving similar triangles to real life scenarios. And when I say real life, I kind of mean real life. One of my friends, he's a surveyor for an engineering company, and he's told me that he uses some similar triangles when in his own job, but mostly some trigonometry as well. And in trigonometry will be our next unit, but it does really relate here, and I kind of came up with an example that kind of demonstrates that. So, our learning goal is to solve problems using similar triangles, of course, that's what we're here for. And just a note here, it says similar triangles can be used to determine lengths that cannot be measured directly. And when we use similar triangles and solve for the length of a missing measure, we call this indirect measurement. It's like, so we've kind of used some other measurements to indirectly measure something that we're actually looking for. Now, when we're solving these types of problems, if you're the person who likes to follow the steps, these are the steps for you. The first step is to draw a well-labeled diagram. Sometimes a diagram might be there, but in which case you might have to label it, which is important. A let statement to represent your variable, of course. Prove that the pair of triangles are similar. It's important that we do that, and most times we do that, it'll be through using angle-angle similarity. So that would be like kind of using alternate angles or opposite angles and things like that, and looking for those types of angle patterns within the pair of similar triangles to prove that they're similar. Now, it's very important that we do prove that the triangles are similar. I'm going to put a little star beside this one, and that's because if we're using the idea that one triangle is proportionate to the other, and that would only happen if the triangles are similar. But really, if they're not similar, then everything we're doing is kind of just incorrect. So it's important that we say, okay, yes, these are for sure similar triangles, and which means that they are proportionate to one another. So that is a huge, important step to cover. Okay? But to you folks, it's like second nature. You know that one like the back of your hand. Now, next, we're going to set up the ratios of corresponding sides. Lovely. We're really used to that. Next, we find the value of the unknown by solving the proportion, whether that's, some of us might be using cross multiplication, but I never have. We just multiply by the denominator of where the variable is, each side of the equation, and kind of solve in that sort of way. And of course, lastly, because the question is asked in words, we should also answer it in words. Okay, so let's start indirectly measuring some stuff here. So here's example 1. A new bridge is going to be built across a river, but the width of the river cannot be measured directly. Can you imagine trying to put a tape measure across a river? Surveyors set up posts, and they did this in a very strategic way. And then they put it at points A, B, C, D, and E. And on the diagram, you can see that it's very likely that the surveys were on this side of the river, because you notice how they put pole A, C, D, and E like that, and this is the only side where you see some measurements. So they must have been on this bottom side here. They take a measurement from A to C, from C to D, and from D to E. Okay, the question is asking, what is the width of the river? Okay, so really, there's one particular side length that we are looking for, and it's the side length that represents the width of the river. I know this diagram isn't, too pretty, but I think you get the idea. There's green grass, and then there's that blue river, and we labeled it river for you in case you didn't know what it was. Maybe it looked like a hot dog or something, but no, it's certainly a river. So this looks like a really well labeled diagram, except it's missing just one thing. It's missing the little x. So of course the x is going to go on side length AB, because this side length AB represents the width of the river. So we'll say, we'll let this x be the width of the river. Great. Now the next step here, really important, is to prove similarity exists. And a lot of the times we're using angle-angle similarity. So if you have a look at this diagram and what is given, we might be able to come up with some statements and reasons for why we believe it's true. First, I say that angle A is equal to angle D, and the reason for that is because they're both 90 degrees. I should put a little degree there. And another pair of equal angles would be angle C and angle C, which sounds a little bit funny, but if I'm talking about this angle C and this angle C, like that, those are equal, and it's because it creates this X, which creates opposite angles. So we can say the reason for that is opposite angles. So triangle ABC is similar to triangle DEC, and the reason for that is angle-angle similarity. Okay, so now that we know that the pair of triangles are in fact similar, we can now go ahead and begin setting up our corresponding side length ratios. Now remember, it's important to be consistent with which triangle, like if you're gonna choose triangle ABC to be on the top, then all those side lengths must be on the top. And also the corresponding side lengths of the smaller triangle should be on the bottom. So it looks like I put triangle, let me just fix these, triangle ABC on top. And some of us might got into the habit of maybe drawing a little box here, putting triangle ABC and then triangle DEC. Like you don't really need what I'm writing here, but some people might like to have it there because it kind of keeps things consistent. So AB, see here, AB corresponds with DE, right? How about BC? BC is this large hypotenuse across from the 90. Well, that's going to correspond with EC. Again, the hypotenuse across from the 90. And once you have two of them, the third one's pretty much just, AC, DC. AC, DC! Hey, I like that one. Okay, now we're going to fill in what we know. So we know that AB is just X, right? We know that DE is 13 meters for sure. BC we have no idea, EC we have no idea. And then our favorite one here, AC/DC. AC is 50 and DC is 9. So from here, we're trying to now solve the proportion. And if you notice, we can use this one here because it's it's a complete ratio, it's a complete proportion. And we're also going to use this one here because, well, that's the one we're solving for. Notice that this one in the middle, there's nothing to be offered to us, so we don't really use it at all. So we set the two proportions equal to one another, and we're going to multiply each side by 13. And when we do that, remember this, like multiply this side by 13, and also this side by 13. This 13 cancels with the denominator, right? When you multiply it by 13 and then divide by 13, you just end up with whatever you had at the beginning here, which is x. And this can go right into our calculator, and we should get it around x equals 72.2. Great. So, therefore, the width of the river is 72.2 meters. And that is how we solve any sort of word problem. Great. We got one more example. Example 2. Shiva is standing beside a lighthouse on a sunny day as shown. So you can see here's Shiva, right? There she is. And here's a lighthouse. Good. She measures the length of her shadow and the length of the shadow cast by the lighthouse. So it looks like Shiva measured her shadow to be 4.8 meters, which is already in the diagram. Lovely. And then the shadow from the base of the lighthouse to where Shiva's shadow and the lighthouse shadow meet. It looks like it's 75 meters. Then they give us one tidbit of info. They tell us that Shiva is 1.6 meters tall. The question asks, how tall is the lighthouse? So it looks like we have a well-labeled diagram already, but there is a few things missing. First, they tell us that Shiva is 1.6 meters tall, so we should go ahead and put that in our diagram, just so we don't miss out, because if we didn't have that information, this question might be a little tough. And then how tall is the lighthouse? We're looking at this side length here. Now, when it comes time to naming side length, like here's the sun, okay. Remember drawing the sun in the top right-hand corner, right? Those were the days. Wow, I kind of miss it. So let's leave the sun alone. If we're talking about these side lengths, like what will we call this side length? Notice how there's not really anything we call these side lengths. So we have to give them names. That's what we're talking about when we say a well-labeled diagram. I mean, this looks like a beautiful diagram, don't get me wrong, but it is missing a few things. So we'll call this point over here L for lighthouse, and let's pretend like this is like, I don't know, this is north. We'll call this point down here N. We'll call this BC, and then we'll call this one, this corner, M for, I suppose that could represent where the two shadows meet. This is Shiva. We could have used S and H or something, but anyway. Notice that each corner, first of all, has a letter, and then also the meeting points of lines. Like, it's almost like every sort of intersection and or corner has a little name here, and we kind of represent those corners or meeting points with letters. So now we can clearly see two triangles. We see triangle BCM, and we see triangle LNM. So, almost a well-labeled diagram. We are missing just one more thing. We're looking for how tall is the lighthouse. So we're looking for side length LN. So we can go ahead and label that with an X. I mean, it doesn't have to be X, but you know, just so addicted to X, I guess. We can go ahead and write, let X be the height of the lighthouse. Okay. Next is to prove similarity. If you're using those steps at the front. Okay, so proof of similarity. Let's say that angle C equals angle N, and that's these little perpendicular angles. Now, it didn't really specify that they were 90, but we're really safe to make the assumption that they're both 90. First of all, because it was already in the diagram, so that was really helpful, but also because someone is standing straight, and the lighthouse is usually built straight, so we just assume that there's some perpendicular angles there. So we can say they're both 90 degrees. And another pair of equal angles would be angle M, yeah, down here. Angle M equals angle M. Kind of sounds a little bit weird, but that's because it's a common angle between both of the triangles, right? If we're looking at this small triangle here, it's got angle M in it. Or perhaps we're looking at this large triangle, it still has angle M. It's a common angle between the two triangles. So therefore, we can say, you know, triangle BMC is similar to triangle LMN, and the reason why they're similar is because of angle-angle similarity. So now that we've proved that these two triangles are similar, we know that there's some proportion between the side lengths. We know that because they're similar. So what we're going to do is set up our corresponding side length ratios. So remember, again, to be consistent with the, let me just show these a little bit better. I don't know why they do that. Is that why? Ooh, definitely not. It's important to keep one triangle on top of another. Like I said, I usually keep the larger triangle as the numerator. I don't know why, I just usually always do. So at the top here, I did triangle LMN. Maybe we can do that. LMN, and then on the bottom I used triangle BMC. I apologize for that penmanship. Okay, now we're going to fill in the blanks here the best we can. Sometimes we don't have anything, like for example LM, we don't have that. And same with BM, we don't have that. Oh, sorry, we didn't really go over which is corresponding. So LM corresponds to BM, of course. MN, this bottom here, corresponds to MC. And lastly, LN corresponds to BC. Just like that. And I'm sure you're already pros at that, and we can see it really nicely there. So we fill in the blanks the best we can with everything that we got. Let me just see this diagram again. Oops. And now we notice that, well, there's nothing here. There's nothing for us to use here. And we have one complete ratio, which is wonderful. And also the ratio that has our variable inside of it. So we're going to have to use these two, set them equal to one another, and we're going to solve this proportion. We're going to multiply this side by 1.6, multiply the other side by 1.6. The divide by 1.6 cancels with the multiply by 1.6. And this left side, it's quite honestly, just put it right into your calculator the way you see it right here. You can do it in one shot. But if your calculator is maybe not the one that holds the display, what you could do is do 75 divided by 4.8, press equals, and leave that number there. Then just hit multiplied by 1.6, press equals, and that should give you the exact answer. If you start rounding in the middle here, you might not get the exact answer. So of course, yes, we have this, put in our calculator, and you should have gotten, where is it? Oh, it's over here. 25 right on, exactly, 25.0. So therefore, the lighthouse is 25 meters tall. And notice how I put in the measure, like meters. We know it's meters, not centimeters or kilometers or whatever. Okay, so folks, that's all we got. There's some great homework down here, page 386 to 387, 2B, 3, 4 BCD, 5, 6, 12, and 13. I had a look at all of them. I think they're great. Number 13 is one of those ones where you kind of gotta think about and kind of look at. It's not one of those ones where you just go ahead. You're just going ahead and solving it. It's one of those ones you got to think about, and it's like, well, what information do I actually need in order to solve these types of questions? It's a really good one. Folks, if you do need anything, please let me know. Use these steps to help you. If I were you doing the homework, I would have this out in front of me all the time, and I'd use it as a guide to completing each question. And remember, proving that the pair of triangles are similar is super important, and a lot of the times, if not almost every single time, in these word problems, we're going to be using angle-angle similarity. Okay, folks, if you need anything, let me know. I'm always here to help.